These are your notes for Unit 3, Day 1 of Calculus. If you would like to see the warm-up, the review question, or any of the test questions we covered in class today, just look at the finished notes. So today we're going to talk about how we can use derivatives to find the extrema of a function. Extrema are the maximum and minimum values that would occur on a graph, so the peaks and valleys, or the absolute highest point or the absolute lowest point that occur on a graph. And those are called the critical points of our function. So extrema of a function. Again, extrema come in a couple different shapes and sizes. We can have local or relative minimums and maximums. And these can be, like on a polynomial graph, they can be the peaks and the valleys. So this could be a local maximum, and this would be a local minimum. So it's not the highest point that would occur on the graph, but within that neighborhood, it's the highest point that occurs. And it's not the lowest point that occurs on the graph, but within that neighborhood, it's the lowest point that occurs. So those are local or relative minimums and maximums. And then you can also have absolute or global minimums and maximums. And those would be the absolute highest or absolute lowest points on a graph. So if you have something like this, and then it ends, this point right here would be the global maximum, because it's the highest point that occurs. And then this point down here would be the global minimum. Even though it's not a valley, it's still the global minimum because it's the lowest point that occurs on the graph. So in our graphs down below, this point right here, this is the point when x is 0 and y is 2, that is a global or absolute maximum. It's also a relative maximum because in that neighborhood, it's also the highest point that can occur. And then these points down here would be the global minimums because they are the lowest values that occur. So at 2, 0 and negative 2, 0, you have global or absolute minimums. On the graph next door, this point right here would be your global minimum. It doesn't have a y value given, so we'll just give it 1. So at the point a comma 1, you have a global minimum. And then this point right here would be the global maximum. So let's just call that the point B4 would be the global maximum. That's the highest point that occurs on that graph. So you have a theorem called the extreme value theorem. So what the extreme value theorem says is it says as long as your function is continuous. So if f of x is continuous on whatever interval you're talking about. So is continuous on an interval from a to b. And the endpoints have to exist as well. So they can't be holes. So if f of x is continuous on a to b, then f of x has global extrema, meaning it has an absolute max and an absolute min on that interval. So as long as your function is continuous, it will have an absolute maximum and an absolute minimum. So if this is my function, then on that interval, we can just call this from 1 to 8. It has a highest high point and a lowest low point. So as long as the function's continuous, there's no holes, jumps, or asymptotes, you're going to have a highest high and a lowest low point. Now, where this really comes into play is when you have a function that looks like this. So it's the same function we did earlier, but now at all of the high and low points, you have open circles. So this would be the global maximum, except for it doesn't exist. So let's say that that was at 4. Well, then what would be the global maximum if at 4 doesn't exist? Well, it would be the next height closest to 4. Well, what's the next height closest to 4? 3.9. Can you get closer to 4? You can, 3.99. You can get even closer, 3.999. Well, what would be the closest number to 4? There is no closest number to 4 because I can just keep adding an extra 9 every time. So there is no global maximum on this picture because there is no exact number that would be the maximum. I could always get closer to 4, so there's no precise exact number that would be the maximum. Same thing with the minimum. The minimum would be 0, but since I have open circles at both of the zeros, 0 doesn't actually exist, so there would be no global minimum as well. So relative or local mins and maxes, we talked about these as well. These are the peaks and valleys on your graph. They can also be cusps and corners as well. They don't have to be rounded, so cusps and corners will also work for this. So this point right here would represent a local maximum. This point right here could be a local minimum. And notice we have a weird cusp or corner right there. That's the absolute maximum. It could also be a relative maximum if it was not the highest point that occurs. Endpoints can also be local minimums, so that's a local minimum. It's the lowest point that occurs within that area, but it's not the lowest overall minimum because that would be right here over at A. So that's just a picture of where local or relative maximums and minimums and global or absolute maximums or minimums could occur. So on this picture, go ahead and tell me what the global max and min is and what any local or relative max and mins are. So tell me the global max or the absolute max, the global min or the absolute min. Tell me the local max or the relative max and the relative min or the local min. All right, well, the global maximum would occur at this point right here, and this was 1, 2, 3, 4. We'll call that 5. So the global max occurs when x is 5, and it is a height of 1, 2, 3, 4, 5, 6, 7. So the global max occurs at the point 5, 7. The global min occurs right here, and that looks to be at the point -2, 1, 2, 3, 4, 5, -2, -5. So that would be my global min. So that is the lowest height that my graph takes on. My local max is this peak right here, and that occurs at the point 1, 2, 3, 4, 5, the point 0, 5. So that would be a local max. It's not the highest point that occurs, but in that neighborhood, it's the highest point that occurs. And this point right there, that little corner, is going to be a local min. It's not the lowest point overall that occurs, but in that neighborhood, it's the lowest point that occurs. And that occurs at 1, 3. And that would be a local or relative min. All right, so how can we use calculus to find those? Well, we're going to use something called critical numbers. Critical numbers are anywhere where the derivative of a function equals 0 or the derivative of your function is undefined. So anywhere where the derivative is equal to 0 or the derivative is undefined, you're going to have a critical number. And remember, the derivative is the slope of a tangent line. Well, the slope of a tangent line is 0 at peaks and valleys, which is what we're trying to find. We're trying to find the local max and mins. And so when the slope is 0, you know you're going to have a local max or min because the tangent line is horizontal. Where is the derivative undefined? The derivative is undefined at corners and cusps because remember, the slope of the tangent line is different coming from the left-hand side and the right-hand side. But you can also have peaks and valleys at cusps and corners. And cusps and corners, again, occur when the derivative is undefined. So you've got some examples over here. So the slope of the tangent line is 0, so f prime of x is 0. And then here the f prime of x is undefined. And here the slope of the tangent line is 0. Here the slope of the tangent line is undefined. Here the slope of the tangent line is 0. It's a critical point, but notice it's not in either a max or a min. We're going to call that a plateau point. Same thing here. Here, if we try to find the derivative, it's undefined because the slope of that tangent line, it's vertical. So, and then that one is undefined as well. Okay, so again, critical numbers occur anywhere where the derivative of your function is either 0 or undefined. So let's look at some examples and try and find the critical numbers. So if we want to find critical numbers of a function, again, we're looking for where the derivative is equal to 0 or the derivative is undefined. So the first step on these problems is we need to find the derivative and figure out where it's 0 or undefined. So the derivative of this function is going to be 2x minus 8. And where does this function equal 0? Well, add the 8 over and divide by 2. And so my critical number is going to be x equals 4. Where is 2x minus 8 undefined? It's undefined nowhere. So the only critical number is when x is equal to 4. On the next one, we'll take the derivative. And the derivative of this one is 4x to the third minus 4x. And we want to know where this is equal to 0. Well, I can factor out a 4x. And I'd be left with x squared minus 1. And so I can factor that further. This would be x plus 1, x minus 1. And where is this 0? Well, it's 0, at -1, and at +1. So those are the three places where the derivative of the function is 0. Where is the derivative undefined? Well, 4x to the third minus 4x is never undefined. So the only critical numbers would be 0, -1, and 1. All right, let's look at the next one. Find any critical points. So again, critical points is when the derivative is 0, undefined. So let's find the derivative. We're going to use chain rule. So derivative of the outside, leave the inside alone, and then subtract 1. So that new exponent would be -1/3, and then times the derivative of the inside. The derivative of 2x minus 8 is 2. So this derivative is going to be, I'm going to have to rewrite it. So this is going to be 4 on top because 2 times 2/3 is 4/3. And then anything with a negative exponent can drop. So this would be 2x minus 8 to the 1/3 power. And that's my derivative. That's my y prime. So I want to know where is the derivative either equal to 0 or undefined. Well, the only place where a fraction equals 0, so if you want a fraction to equal 0, you need the numerator to equal 0. Well, in this case, my numerator is 4. Where does 4 equal 0? It never equals 0, so my derivative is never going to be 0. For a fraction to be undefined, you need the denominator to equal 0. So we want to know when the denominator of this expression is going to equal 0. So we want to know when 3, and this is going to be the cube root of 2x minus 8, to the 1/3 power is a cube root. We want to know when that equals 0. So let's solve this. We're going to divide by 3 and divide by 3. And then we have the cube root of 2x minus 8 equals 0 divided by 3 is 0. And then to get rid of a cube root, we're going to cube both sides. So cube both sides, and 0 cubed is 0. So now I have 2x minus 8 equals 0. I'll add 8 to both sides. And 2x equals 8. Divide by 2, divide by 2. So the only critical number for that function would be when x is equal to 4. All right, let's look at the next one. If I want to take the derivative of this one, the derivative is going to be chain rule on both parts. So multiply by the exponent. -1/5 times 5/3 is going to be -1/3, and then x minus 4 to the 2/3, and then times the derivative of the inside is 1. And this is not product or quotient because I'm subtracting. So now I'll multiply by the exponent. So -4/3, leave the inside alone, x minus 4, and then subtract 1 to the -1/3, and then times the derivative of the inside is 1. And so if I were to rewrite this, I would have negative x minus 4 to the 2/3 over 3 minus 4, and then 3 times x minus 4 to the 1/3. Now, unfortunately, I have two fractions. In order to combine them, I need a common denominator. So the common denominator is going to be 3x minus 4 to the 1/3. So I need to multiply this first fraction by x minus 4 to the 1/3. And so now I have the derivative is going to equal. My denominator is going to be 3 times x minus 4 to the 1/3. And now my numerator, notice, these two guys have the same base, x minus 4 and x minus 4. And I'm multiplying them, so I can add their exponents. 2/3 plus 1/3 is just 1. So this is going to be 1 x minus 4, and then we have the minus 4 in the other numerator. So my derivative, once I simplify it, is going to be negative x, and then negative times a negative becomes positive 4. So positive 4 minus 4 goes away, so I just have negative x over 3 times x minus 4 to the 1/3. Now it's a fraction. My derivative is a fraction, so now I want to know when the derivative is equal to 0 or undefined. Remember, a fraction is 0 when the numerator is 0, so either the numerator is equal to 0, and it's undefined when the denominator is equal to 0. So 3 times x minus 4 to the 1/3 equals 0. Well, I'm going to have a critical number when x equals 0 from solving the first one. And then the second one, divide by 3, and x minus 4, I'm going to do the cube root of that, equals 0, because to the 1/3 power is a cube root. Then I'll cube both sides. 0 cubed is 0, so I have x minus 4 equals 0. Then add the 4 and add the 4, and x is equal to 4. So my two critical numbers on that one are going to be 0 and 4. All right, so again, critical numbers occur when the derivative is equal to 0 or the derivative is undefined. So finding actual relatives mins or max using derivatives. We call this the first derivatives test. So let's just start with the function we know. So f of x equals x squared minus 4x plus 6. So we know that this is going to be a happy parabola because it's a positive x squared. So what we're looking for is we're going to be looking for this point right here, which is going to be a local or relative minimum. So we're going to be looking for a minimum. To do that, your first step is you need to find the critical numbers. So find when f prime of x is equal to 0 or undefined. So if we actually want to find relative mins or maxes, first we find the critical numbers. So let's find when this derivative is 0. So f prime of x is going to equal 2x minus 4. And where does that equal 0? Well, add the 4 over, 2x equals 4, and then divide by 2. My critical number is going to occur when x is equal to 2. Okay, so step 2 is now we're going to make a sign chart. Because we need to decide, are my critical numbers mins, maxes, or neithers? So when x is equal to 2, do I have a minimum, a maximum, or neither? Well, how can I tell? Well, if we're looking at that parabola right here, what's going to be true about all the tangent lines before 2? Well, the slopes of all those tangent lines are going to be negative. So all of the derivatives on the left-hand side of that minimum should be negative. And then after the 2, notice what's going to be true about all the tangent lines there. Well, all the tangent lines are going to have a positive slope. So when the derivative changes from negative to positive, you have a minimum value because the slopes were going down and then they're going back up. So you would have a minimum if in your sign chart, the derivatives change from negative to positive. Well, what if it looks the other way? What if it looks like this? So to have a maximum before your critical number, so before the derivative is 0 undefined, your slopes need to be positive. So the slopes of the tangent line should be positive. And then afterwards, the slopes of your tangent line should be negative. So the derivatives need to change from positive to negative, and then you would have a maximum value there. What if the derivatives don't change signs? So it looks like this. So here, notice we have a slope of a tangent line equals 0, and before that the slopes are positive, and then after that the slopes are positive. We call that a plateau point. So it plateaus for a little bit, but then it keeps going. So that would be the neither. So we have our critical number 2. We're going to put that in our sign chart. So we'll put 2 in our sign chart. And then we want to know what's happening to the derivative before and after that. So we could pick 0 and we could pick 10, and then we plug it into the derivative. The derivative is 2x minus 4. So if I take 0 and plug it into 2x minus 4, I get a negative value. If I take 10 and plug it in, I get a positive value. So my derivatives were negative, so my graph was going down. Then it has a horizontal tangent line, so it levels off. And then my derivatives were positive after that. So notice that would represent a local or relative minimum on the graph. So we have a local or relative minimum when x is equal to 2. If you want to figure out what the height of that local or relative minimum is, you take the x value and you plug it back into the original function because you want to know what the height of the original function was. So if I take 2 and plug it back in, I get y equals 2 squared minus 4 times 2 plus 6. So this would be 4 minus 8 plus 6, which would be negative 4 plus 2, so it would be 2. So my local or relative minimum is going to occur when x is 2 and y is 2. So that would be the minimum of my parabola would occur at the point 2, 2. So again, to find relative mins or maxes using derivatives, you find where the derivative is 0 or undefined, and then you make a sign chart. If in your sign chart the derivative changes from negative to positive, that would represent a minimum. If the derivatives change from positive to negative, that would represent a maximum value. If the sign doesn't change, then that would be a plateau point. So let's look at more examples. My derivative here would be 3x squared plus 2x minus 1. To find the critical number, set that equal to 0 and solve. So this would be 3x, and then I need a positive 3, so plus 1 and minus 1. So my two critical numbers are going to be 1/3 and negative 1. So I want to decide, are they negatives or positives? So we'll make a sign chart, negative 1, positive 1/3, 0 and 0. And then I have to test the derivative before that, so negative 10, in between them 0, and after that we'll test it at 10. So if I plug into 3x minus 1 times x plus 1, if I plug in negative 10, I get a negative times a negative, which is a positive. If I plug in 0, I get a negative times a positive, which is negative. And if I plug in 10, I get a positive times a positive, so a positive. So let's see what's happening here. Here, my derivatives were positive, and then they were 0, and then they were negative afterwards. So positive to negative. So when x is equal to negative 1, I have a local maximum. And then at 1/3, the derivatives before were negative, the derivatives after were positive. So if my derivatives change from negative to positive, so going down to going up, that represents a minimum. So at x equals 1/3, I have a local minimum. And then if I want to find the actual points for my local min and local max, I would take those values and plug them back into the original function. So if I plug in -1, then I get -1 cubed plus -1 squared minus -1. So this would be -1 plus 1 plus 1, which would be 1. So I have a local maximum at the point -1, +1. And then I could take 1/3 and plug it back in, and I would get 1/3 cubed plus 1/3 squared minus 1/3. So this would be 1/27 plus 1/9 minus 1/3, or 1/27 plus 3/27 minus 9/27, which would be -5/27. So I would have so this is my local max, I would have a local min at the point 1/3 -5/27. All right, let's look at the next one. So this should be a happy parabola, just looking at it. So this is f prime of x is either equal to 0 or undefined will get us our critical number, so 2x minus 8. So if I solve this, I get x equals 4 as my critical number. Now I'll make a sign chart. If I want to look at the derivative before and after that, I could look at 0 and 10. If I plug 0 into my derivative, I get negative numbers. If I plug 10 in, I get positive numbers. So my derivatives go from negative to positive. So my tangent lines go from going down to going up. So this would be a local minimum. So my local minimum occurs when x equals 4. And if I take 4 and plug that back in, I would get 16 minus 32 minus 10, which is -26. So my local minimum would occur at 4, -26. All right. We already found where these functions would have local extrema. So we found earlier where the derivative was equal to 0 or undefined. So I'm just going to scroll back up and figure out where we found our local mins and local maxes. Or sorry, where we found our critical numbers. So for the first one, we have a critical number when x is equal to 4. So let's scroll back down. And we know we have a critical number. So f prime of x is equal to 0 or undefined. I believe it was undefined when x is equal to 4 from our work up above. So now we're going to take 4 and we're going to plug it into the derivative. And my derivative, I knew I was supposed to write it down. My derivative was 2/3 2x minus 8 to the -1/3 times 2. So it was 4 over 3 times the cube root of 2x minus 8. So that was my derivative. So we will test it at 0 and 10. If I took 0 and plugged it in right here, I would get 2 times 0 minus 8. So I would get the cube root of -8, which is negative. And so 4 over 3 times negative, those would give me negative numbers. If I took 10 and plugged it into the derivative, I'd get 2 times 10. So 20 minus 8 would be 12. If I took the cube root of 12, I'd get a positive number, and everything else is positive, so I'd get a positive. So my derivatives went from negative values to positive values. So at x equals 4, we would have a local minimum. And if we wanted to figure out what the local minimum was, we would take 4 and plug it back in. And if I took 4 and plugged it in, I would get 0 to the 2/3, which is 0. So I have a local minimum at the point 4, 0. On the next one, we had the derivative, once we simplified it, let's scroll back up, we had the derivative was equal to -x over 3 times x minus 4 to the 1/3. So -x over 3 times the cube root of x minus 4. Maybe that's what it was. Let's scroll back up. -x, yep. And then we found our critical numbers to be 0 and 4 for that guy. So critical numbers at x equals 0, x equals 4 were my critical numbers. So we're going to put those in the sign chart. So 0 and 4. We know when we plug in 0, we get a 0. And if we plug in -4, it's undefined because that made the denominator 0. So let's do our test points. We could test -10, we could test 1, and we could test +10. If I took -10, and again, we're plugging them into the derivative, I would get a positive over a negative, so those would be negative. If I plugged in 1, I'd get a negative over a negative, so those would be positive. And if I plugged in 10, I'd get a negative over a positive, so those would be negative. So if my derivatives go from negative values to positive values, that's a minimum. So at x equals 0, I would have a local minimum. And then my derivatives go from positive to negative, so that would represent a maximum. So at x equals 4, I have a local maximum. And again, if I wanted to know what the y values were, I'd plug them back into the original function. So that's how you can find local or relative mins and maxes. Find where the derivative is equal to 0 or undefined, and then make a sign chart to figure out how the derivative is changing signs. What about global extrema? So what if we want to find the absolute highest or lowest value on a graph? I apologize, the mailman just got here. So if we wanted to find the absolute highest or lowest point on a graph, it's basically the same steps, but then they also have to give you an interval to check on because we have to check the endpoints. So our steps are, we have to find where f prime of x is equal to 0 or undefined. So we're finding the critical numbers. We make a sign chart. Actually, on these, we don't have to make a sign chart. We don't need to know if they're minimums or maximums. Then you're going to take the x values from number 1 and the endpoints that were given and plug them into and substitute them into f of x, the original function. The highest y value, the biggest value you get is going to be the max, and then the lowest y value that you get is going to be the global min. So that's how you're going to find your global mins and maxes. Figure out where the derivative is equal to 0 or undefined, and those are your critical numbers. And then you're going to take your critical numbers and the endpoints and plug them all back into the original function. The highest value you get is going to be the global maximum, and the lowest value you get is going to be the global minimum. So let's do that. So first we're going to find the derivative. My derivative is equal to negative 3x squared minus 12x minus 9. I want to know where that's 0 or undefined. Well, it's only going to equal 0, so I'm going to factor out the 3, negative 3, and I get x squared plus 4x plus 3 equals 0. And so this is going to be x plus 3, x plus 1 times negative 3 equals 0. So the two critical numbers are going to be negative 3 and negative 1. So I'm going to take negative 3 and negative 1, and then I'm going to take my endpoints. So my endpoints were x equals negative 4 and x equals 1. And I'm going to plug all of these back into the original function. So I want to find f at negative 4. I want to find f at negative 3. I want to find f at negative 1. And I want to find f at 1. So I'm going to find my original function at all 4 of those x values. The biggest y value I get will be the global maximum, and the smallest y value I get will be the global minimum. So if I take negative 4 and plug it in, I would get negative 64 and then times the negative, so I would get 64. I'm just going to do these on Desmos so I don't make any little math mistakes as I'm going along. So I have y equals negative x to the third. Oops, negative x to the third minus 6x squared minus 9x plus 3. And then we want to figure out what this is when x equals negative 4. So x equals negative 4. Oops. So x equals negative 4. So at x equals negative 4, I get negative 25. At x equals negative 3, I get negative 21. At x equals negative 1, I get 0. Nope, sorry. When x equals negative 1, I get negative 1. And then when x is equal to 1, I get -5. So the biggest between -4 (x squared minus 6), minus 9x. That would be helpful if I would have put the original one in. There we go. So sorry about that. I'm going to have to redo these. So these are not the right because I forgot the 9. So if I did this, if I plug in -4, well, sorry, if I plug in 1, I get -13. If I plug in -1, I get 7. If I plug in -3, I get 3. And if I plug in -4, we get 7. So the global maximum are going to be these 2 points. So I get global maximums when the height is 7. So this is a global max and a global max. So my global max is 7, the height of 7. And then my global min is -13. That is the lowest that the graph will go. So again, to find global extrema, you find the critical numbers. So find where the derivative is 0 or undefined. And you take those numbers and the endpoints that the problem will give you and plug all of those x values back into the original function. The lowest y value you get is the global minimum, which in this case was -13, and the highest y value you get will be the global maximum, and in this case it would be 7. All right, let's find the absolute or global extrema of the following. So we need to find the critical number, so we're going to take its derivative. So using quotient rule, derivative of the top is 2x, then times the bottom, 3x minus 6, then minus the derivative on the bottom is 3, and then times the top is x squared over the bottom squared, 3x minus 6 squared. I'm going to simplify the numerator into 6x squared minus 12x minus 3x squared, all over 3x minus 6 squared. Simplify it one more time, and we get 3x squared minus 12x over 3x minus 6 squared. All right, so my derivative is a fraction. I want to know when the derivative is 0 or undefined. A fraction will equal 0 when the numerator is equal to 0. So we want to know when 3x squared minus 12x equals 0. And a denominator is undefined when the denominator is 0. So we want to know when 3x minus 6 squared is equal to 0. Well, in the first one, I can factor out a 3x, and I get x minus 4. And so my critical numbers for my numerator equaling 0 are 0 and 4. So I need to test 0 and 4. And then 3x minus 6 squared equals 0. So either 3x minus 6 or 3x minus 6 is equal to 0. So x is going to equal 6 over 3 is 2. So my critical numbers are 0, 4, and 2. But I only want the numbers on the intervals 3 to 6. So I want to go between x equals 3 and x equals 6. So the only ones I'm going to test, 2 is out and 0 is out because they're not on the interval. I'm not sure if I checked up here. I wanted to be between -4 and 1, and we were good. All of those worked. Okay. So I'm not going to use 0 or 2 because they weren't on the interval that we wanted it. We wanted to be when 3 is less than or equal to x is less than or equal to 6. So I'm going to use 3, 4, and 6. So I'm going to take those and plug them back into the original function. So I'm going to test out 3, I'm going to test out 4, and I'm going to test out 6. So if I'm going to go back to, well, nope, these aren't that bad. So if I plug in 3 into the original function, I would get 9 over 9 minus 6 is 3, so that would be 3. If I plug in 4, I get 16 over 12 minus 6 is 6, so this would be 8/3, or it would be 2 2/3. On the next one, if I plug in 6, I would get 36 over 18 minus 6, so 12, so this would be 3. So the global max, the greatest height that this would take on, would be 3. And the global min, the smallest height that this would take on, would be 2 2/3, or 8/3. So that would be my global max and global min for that problem.